Welcome to the AI Research Roundup. I'm Alex. Today, we are looking at a paper from the Hugging Face trending list, published on March 4th, 2026, just 2 days ago. It introduces a framework that makes training large language models for scientific discovery mathematically tractable, effectively reducing the search complexity from exponential down to logarithmic. The paper is titled, Moose-Star Unlocking Tractable Training for Scientific Discovery by Breaking the Complexity Barrier. And as we will see later, the model shows some really exciting improvements, with significant implications for overcoming the complexity wall in automated research. And for those interested in the implementation, the authors have shared their code on GitHub. So on Hugging Face, you can grab the 8 billion parameter weights for both models. These pages include Python examples for composing hypotheses and retrieving inspirations for your research. Okay, diving into the mechanics. Figure 1 illustrates a core concept called bounded composition. The large dashed rectangle represents the vast global knowledge space, which contains millions of papers. Instead of forcing the system to find one exact, perfect inspiration, marked by the center point, the authors define a semantic tolerance zone, shown by the concentric circles. By training the model to build hypotheses using related proxy papers that fall within this zone, the framework significantly relaxes the retrieval task. Finding any acceptable paper in that bounded space is much faster, which more than makes up for the slightly harder job of reasoning through the final idea. So, Table 2 measures how this bounded training impacts hypothesis composition. The baseline R1 distilled QN7B model achieves a total score of 4.3. The fine-tuned Moose-Star model boosts this past 5. More importantly, adding copies of bounded data, which means training on those noisy proxy papers, pushes the total score even higher. This shows that exposure to semantic variations during training improves overall reasoning robustness. Alright, turning to the retrieval side of the framework. Table 1 details the inspiration retrieval accuracy. The baseline R1 distilled QN7B model achieves about 28% accuracy. However, after being fine-tuned on 152,000 examples, the specialized Moose-Star IR7B model nearly doubles that performance, reaching roughly 54%. This substantial jump highlights how effective the decomposed training approach is for finding relevant inspirations in a vast knowledge base. Well, Figure 2 tracks how performance scales as we feed more training data into the hypothesis composition model. Interestingly, the model exhibits a distinct threshold behavior. The improvement over the baseline stays relatively flat until the dataset size hits 1,000 samples, after which we see a sharp log linear jump. This happens because hypothesis composition is a complex generative task, which requires a critical density of data before the model starts synthesizing meaningful scientific connections. Okay, Table 5 illustrates why this new framework is necessary. The top rows show the results of trying to brute force the discovery process end to end. As the required reasoning steps increase from 1 to 3, the success rate collapses to 0%. This combinatorial explosion makes traditional training practically impossible. In contrast, the bottom row evaluates the decomposed hypothesis composition module. By isolating the problem into single guided steps, it maintains a robust pass rate of 47%, which finally makes training mathematically tractable. So, Figure 3 compares how this framework scales at test time against the brute force approach. On the left, Moose-Star achieves 100% success in under 6,000 inference steps, while the baseline stalls at about 41% despite using more compute. The right chart breaks this down by problem complexity. As the required reasoning steps increase to 3, Moose-Star wins 92% of the time, successfully bypassing the complexity wall that breaks traditional methods. Alright, wrapping up. Moose-Star proves that by decomposing the scientific discovery process, we can reduce an impossible exponential search down to a manageable logarithmic one. This breakthrough finally unlocks scalable generative reasoning for automated research. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.